Okay, so on to the next one, porting code to heap. And I should say that initially, I think we thought of this presentation mostly as porting from CUDA to heap, but now we are purposely just thinking of this as porting to heap because as now AI workloads are becoming more popular, now we want to see this also as being applicable for porting from Python to heap, for instance. Um, but in general, we have several tools that we offer with Rockam that you can use to convert your CUDA code from CUDA to HIP. And those are the HIPification tools, as we call them. So Hipify, basically, Hipify that comes in two flavors, as I'll show you next. Or there's a technique that has had quite a bit of success among our customers. We've been hearing that they like it quite a bit, which is the hippie fly method, where basically you have this header file that intercepts on the fly the CUDA API calls and swaps them with HIP API calls. So the advantage of that, one reason why people like it is that they can just keep the CUDA code as the unique source, and then they don't need to maintain a CUDA and a heap version. So I'll tell you more about that next. But the main takeaway of this slide is that there are several approaches that you can select and that we support. And in general, porting is relatively easy. Obviously, if you have many custom calls that may not be supported by HIP from CUDA, then it may be a little more cumbersome, but eventually it will work out. So going back to the Hipify tools, the ones that I'm going to cover here mostly are Hipify Perl and Hipify Clang. Hipify Perl is the one that we recommend for a quick scan of your project. It's basically a string replacement, not exactly a string replacement, but what it does is basically replaces CUDA instances, CUDA strings with HIP. Um, and it's not gonna test your code, so it's your responsibility to then make sure that there have not been any mistakes or typos or anything that is not going to make it compile. Hipify Clang is more robust in that it generates warnings and has more additional analysis that it offers, but it's a little more involved since basically you have to use it as if it was Clang with the necessary includes and so on. So yeah, for example, Hipify Perl is it's in the bin when you install Broken and can be used for instance like this. So you do Hipify Perl, you um, you type the CUDA file, and then you just send this to a new file that's gonna be in CPP format with your heap kernels, basically. For what concerns Hipify Clang, it's also in the bin directory of your Rockam installation. And you see that this is an example of using it where you have to supply the include, for instance. Here we're just reporting a few experiences concerning hipification that we heard from our clients. For instance, it can be as quick as just an afternoon of work, but it can also take a couple of days, just one single day, or maybe a couple of weeks. And that depends really on the complexity on your code, whether it relies on specific CUDA API and so on. But you see that we have many codes that have been successfully ported, and there's also, this is actually a growing list. Yeah, other tools are the recursive directory tools that you can find in the bin. But I should also say that we have found that LLMs are actually very good at porting code to heap. As I was saying before, not just CUDA to heap, but even Python, because we have seen that Python codes can actually gain a lot of performance when they're ported to heap, specifically the most demanding kernels, of course, because Python has a lot of overhead, or it has a lot of kernel calls that with the heap kernel you can fuse. And so you do less calls, and therefore there's less overhead. And therefore, we also now talk about LLMs as a way to heapify your code. For what concerns the gotchas, and this specifically refers to the heapify tools that we just talked about. As I said, they don't check for correctness. You have to watch out for hard-coded warp size variables, such as 32, for instance. If you're coming from CUDA, you can grep on 32 just in case. And some functions from CUDA may not exist in heap, and heapify also can't handle inline PTX assembly or CUDA intrinsics. But once you're aware of this, you can work around it. So you have to keep these in mind. For what concerns the heapify method, this is just a screenshot of what the include file looks like. And as I said before, one reason why people like it is that it allows them to have a single source of their code. So they just keep the CUDA source and then basically swap the calls on the fly when they want to run on AMD. As you can imagine, this approach works only if there's an exact one-to-one correspondence, and performance needs to be evaluated on a case-by-case basis. But it's a good option to have available, and quite a few sites we know are using it. So something else that's important to be able to handle, and most of the times is actually the tricky part, is the portable build system. Because once you have heapified your code, you want to be able to have a build system that will let you compile it on AMD when you want to compile on AMD, or on NVIDIA when you have an NVIDIA GPU available. So focusing for now on the make file, we have examples of these, by the way, in our examples repo, so you can work on those. And I should also say that we have played with LLMs, asking them to create portable make files for us, and the results were positively surprising. So that's one more way you can leverage those for your heapification. But in this case, I'm showing you a makefile where we are defining this variable heap platform that's defaulted to AMD. And if that's set to NVIDIA, basically you see we're going to set the compiler flags so that the compiler knows it's going to be CUDA with this -x. We still have to supply the include path for ROCm. And if it's AMD, then we do the -x heap. So if we want to use it, we're going to load the ROCm module, assuming it's installed. And if we run with CUDA, if we run on NVIDIA GPUs, we still have to load the ROCm module, because see here, we are leveraging the heap path for the include. So that is what sets what's set by the ROCm module. we load CUDA, and then we specify the heap platform as NVIDIA when we do the make. The CMake, of course, is a little more involved, but the idea is basically the same. With this GPU runtime, we switch between AMD and NVIDIA. And there's also this enable language that's available on CMake that will basically tell if it's HIP or CUDA. Yeah, and the way you actually compile it is basically similar, except that now with CMake, you have to use this syntax with the dash D. Okay, so it's important to be aware of a couple of CMake variables that should be used in your build. So one is CMake heap architectures. And this GFX architecture is basically the target that you want to build. And you can find that with ROCm info as we are showing here. So you didn't have to memorize it. Oh, sorry. With ROCm info, you can find the GFX architecture on the system. So if you want to cross compile, then you'll have to specify the one you want. But if you always want to compile for the one you have on the system, then you can auto detect it with ROCm info. Yeah, and just a little note at the end for Fortran. So we don't have an equivalent of CUDA Fortran. So there's a couple of ways you can leverage HIP in your Fortran code. One is through HipFort, which basically is an interface that's provided by ROCm for the most popular math libraries. So that will allow you to call the HIP API from Fortran basically. And HipFort is the interface that makes that possible. But if you have custom kernels that you want to call that are HIP kernels and you want to call them from Fortran, then basically you're going to have to go ahead and build your own interface. So the thing to do is to port, so if you have CUDA Fortran, then you're going to have to port it to HIP. And then you create a little wrapper, and then you leverage the ISO-C binding module in Fortran to call them from Fortran, basically. We have several examples in the repo that you can get inspiration from if you want to try that. And there's actually a talk that I think is tomorrow about that. Okay. So yeah, we have exercises for this that sit on the Hippify, Hippify, and HipFort directories. And yeah, just gonna give it back to Bob right now. Thank you for listening.
A little bit of a break here to do some of the exercises and catch up. Our schedule has porting exercises at 14:15 afternoon break, and we'll resume at 14:45 with OpenMP and HIP interoperability. Giacomo, are you going to do that one, or is it getting too late there?
No, I can do it. I can do it. I like working at night, so this is perfect for me.
Okay, let's take some questions here. We have in the chat 2 questions. Do you see those, Giacomo? I'll repeat.
Yes.
When I
have, oh, go ahead.
No, you go ahead.
Excuse me, Bob. When I have multiple CUDA code files, how can I translate the multiple files simultaneously? In my understanding, only one file is translated using Hippify Perl or Hippify Clang. So so you can use that recursive option that will basically heapify all the files in a specific directory if you want to do them all at once. Let me share a screen real fast. So I actually went pretty fast on that specific topic, but if you look at the bin of your Rockham installation, there's this there are these recursive directory tools that basically will take care of multiple files at once in your directory. So you don't have to do it for each one of them. And sorry, let's see what was the other question. Would it be possible to install Heapify on NVIDIA GPUs? I think so. If you can install ROCm, then yeah.
We actually did a workshop on portability of HIP code with Oak Ridge and with NERSC. NERSC is running NVIDIA GPUs and Oak Ridge is running AMD GPUs. So NERSC installed ROCm on their system. And so we actually ran the exercises and we could run on either system with what we're showing you here. Now, generally, then the next step is optimization. And optimization, you have to do more optimization with AMD GPUs. They have a smaller cache. They do scale better, but you have to do more work up front. The cache on NVIDIA is larger. So once you did that optimization, it would also speed up the CUDA code. You know, we got pretty comparable performance on both systems. So we wanted to demonstrate portability, and you can do it. If you're going the other direction, you have to install the CUDA header files on AMD system to be able to compile for the NVIDIA GPUs. But it is very effective, and if you want to try to do that, we've had several sites do it. It's a little bit of an effort to get the software installed such that it works.
Yeah, and we have heard interesting stories about portability where some people were running they were used to run their code on NVIDIA, and then they tried it on Frontier, and because NVIDIA software is so mature, it was masking a lot of little issues that they had in their code, and with our compilers they actually found some errors that they had in their code that were somehow mitigated by the NVIDIA stack, and so it actually ended up helping the performance overall on both AMD and NVIDIA GPUs when they found those mistakes and corrected them.
Yeah, this can be effective porting between the two of them at a fairly massive scale. The AI libraries will use Hippify to translate all the kernels over to HIP so that they can compile for the AMD GPU. And so they've got hundreds of routines they just compile on the fly to build for the ROCm software stack. So it's heavily leveraged in many large applications. The key is you can't do crazy things in your code. It's got to be clean CUDA code, not where you're using PTX assembler level or some other crazy stuff. Good questions. More? Anybody else got a question?
Thank you for your questions.
Thanks for the answering. This is Chunghan. Yeah, I have one more question about that. In summary, in my understanding, when I install the ROCm on NVIDIA servers, I can translate the CUDA code using the recursive such kind of the big the bunch of the CUDA code. Yeah, let me try the such kind of way later. Yeah, thank you so much.
Yeah, of course, no problem.
Yeah, so we talked about HIPAA fly versus HIPAA-fy. So there are some code projects, they don't want to modify their source code, but they want to run on AMD GPUs. So they can just add the HIPAA fly header and not have to change anything else. And so if you want to stay CUDA, but compile for AMD, HIPAA fly makes a lot of sense with the header file. If you want to convert over with AMD being the more primary code, then the HIPAA-fy approach makes more sense. Okay. Exercises. Pop those up.
Thank you. And please, if there's anyone that didn't or couldn't access the cluster, ping me in the chat. Hopefully everybody was able to log in.
So I want to point out with the exercises, there are two files that you should have available. One is a PDF that was run through LaTeX. So it's very nice format, but sometimes the lines run off the end of the page. So the other one is an HTML. Doesn't look quite as nice, but it doesn't run off the page. So here's the HTML. And you can see there are a lot of OpenMP language constructs. Now we're into the HIP exercises and the HIPAA-fy examples. So these are the HIPAA-fy examples are pretty quick to do. And we like to describe it that HIPAA-fying the code can take just a couple hours. Converting your make file will take days because HPC applications have such ugly build systems. And if you're working on some of the exercises and you want to see the cheat sheet of how to run them, if you're running into trouble, there is a directory at the top level of the examples called tests. And it has tests for most of the exercises that we have in this in these workshops. It's got 330 tests. So what we do when we bring up a system is we run those tests to see what is functioning on the system. It's not a performance test, it's really a functionality test. So look in that directory and see how each of the examples are run, or run it on your system.